All right, we're now on air. We'll start off by introducing ourselves. I'm Kevin Seeger.
Bradley Castleman.
And Rene Orozco.
All right, and today we're meeting for week 4, lesson 6 in our group meeting quiz. I wanted to ask just really quickly before we get started on that quiz, does anybody, what did you guys learn from the chapter reading so that we can put this into the quiz as well?
For me, the biggest thing, other than a couple rules that we learned, how to work out the z-score and the area, a sample size in the normal distribution module.
Perfect. Okay, so now we're going to take that and we're going to go into this. Let's see what we can do. Okay.
In fact, let me, I don't know if this would be a good thing for us to use today or not. I created a little spreadsheet.
Okay.
I can give to you guys later if you want. I'll show it to you real quick here. Okay, can you see that?
Yes.
Yeah.
So this is a handy little thing here where if I change any of these values in green, like change the standard deviation to 10, the x variable to 30 or whatever, it calculates. This is part of the equation here, the top part and the bottom part after this square root divided by the standard deviation. A z-score here.
Mm-hmm. Man, that is super nice. Well done.
Thank you.
Yeah, so I don't know. I don't know if that'll be loud on like exams though. So I think we should probably learn how to do it longhand.
Yeah. So the last. Oh wait, this is math class. That was an accounting exam. Never mind.
I know it's easy to get mixed up, especially when you have a bunch of math classes.
Yeah. Yeah. No. So, do you have the page up for the? I'm so sorry for the chapter, because I know that there's a longhand description in the chapter. Like shows the equation.
I was just pulling that up. Although I can show you the equation if you want.
Yeah, that's fine. Either way, if you already have it set up and you can write it out, that's fine. That works too.
I'm pretty comfortable with it. It might be a good review for me, actually, if you guys want me to show it to you.
It'll actually be a good review for all of us, I'm sure.
Let's do that real quick then. So share screen, pull up Paint. Okay. Sorry about that. Everything on my side just crashed a little bit.
Oh, that's okay.
So I'll just repeat myself.
Go ahead.
I don't know why this is even coming up. Hang on. All right. So in most cases, we're going to be solving for z, but in other cases, we'll be solving for x, just depending on how the question is worded. So in solving for z-score equals the x variable minus mu, right, which is the mean. Is what mean. okay, over I forget what this thing is called, but basically it's
Sigma.
okay, but the what?
Sigma.
Sigma. Thank you. And but in this case, when we have the sample that we're dealing with, we divide the sigma, or the standard deviation, by the square root of the sample of 25. That would go in here. Okay. So
I think they normally put n.
oh, yeah, that is the value
Size.
n, right? That's the wrong n. Lowercase n. Right. All right. Yep. So a couple things about this, if I remember right. There are two rules that we need to keep in mind to determine whether or not we can utilize this formula to determine the a normal variation, or a normal deviate. No, a normal.
Not normal.
Normal or not normal, but I'm trying to remember the word, or distribution. Normal or not normal distribution. And there's two rules that they use. You guys might have to remind me the name of the rules. One of which, actually the first one is, if you're taking the data from a chart, or excuse me, data that's already, like, if your data comes from a normal distribution, then your normal is going to come out as normal distribution, right?
Mm-hmm.
But if you have something that's skewed right or left, it's not normal, then it's going to depend on two things.
Mm-hmm.
One, it's going to depend on your sample size. And two, it's going to depend on the structure of the data. I forget the two names of those rules. Do you guys remember?
Yeah, I'm looking them up. So there's the central limit theorem.
That's
the
the
law
one that has
of-
to.
And the
Mhm.
law
Right.
of large numbers.
Yep.
Right. So I think the law of large numbers has to do with the sample size, right?
Yeah. The law of large numbers.
I heard
Both of them have to do with the sample size. The central limit theorem, as the sample gets bigger, it becomes a normal distribution. As the sample is smaller, it becomes not a normal, and it's skewed one side.
Mm-hmm.
Yeah, and the other thing to remember about that one is the larger the sample, the more accurate the mean. And you'll see that word used, accurate. So accurate has to do with that rule.
Actually, accurate is with the law of large numbers. Approximate is with central limit theorem.
Oh no.
Okay.
Sorry.
I think what we'll do to remember that is that approximate comes with like the central limit. So approaching
Mhm.
the central limit. So approximately the central limit would make it a little bit easier. I don't know if that helps you guys or not. But the law of large numbers is like a decree, like it has to be absolute.
Mhm.
So with the law of large numbers, that's when we have the more we have the smaller mean, or the more yeah.
Mm-hmm. So it says particularly here, the law of large numbers states that that if the sample size is large, then the sample mean will typically be close to the population mean.
Right. Close to the population mean. Right. That's what I was driving at. Okay.
Yeah, because they said parent over and over again in the video.
Uh-huh.
So it's like you get those mixed up. So parent or population makes sense.
And that's the law of large numbers.
Yes.
Okay.
Okay.
So the central limit theorem states that the sample size is large, then x will be approximately normal. So I'm assuming that the distribution will be normal. But if the law of large numbers talks about the mean being close to the population, yeah, the sample mean will close to the mean, the population mean.
Larger the number, the closer to the population mean.
Mm-hmm.
And when it comes to, I know I'm backtracking a little bit here, but when it comes to the sample size and determining whether it's standard or not, you know how they say with a small sample, it's impossible to determine whether it's standard.
Mm-hmm.
Sample size is standard, but then with larger numbers, you can do it, right? So what is the magic number where it breaks?
Oh, it says for this course, if n is greater than or equal to 30, we will say the distribution of the sample means will be approximately normal.
And that's what the guy said in the video as well. So,
so it says here,
awesome.
Bottom of the book, bottom of the chapter that we were studying was section 6, says 30, equal to, greater than.
Okay.
Okay.
All right. So that's
Now
kind of what I got from the reading and the exercises.
Mm-hmm. Okay. Oh, that's not what I wanted. Go away. All right. Well, that's perfect. Now that we understand those two rules, that's what the quiz is going to be talking to us about. I popped it open a little bit earlier. Was looking into it. So we have the chapter open. We have the understanding of how to find the numbers. So let's go ahead and get started.
All right.
First two questions.
Opening the quiz right now.
Mm-hmm. First two questions are always the hardest. So just remember that, you guys.
My internet is always so slow while we have the live streaming going.
Sorry about that.
It's not your fault. Okay, so this is 6 group meeting quiz, right?
Uh-huh.
Okay. I'm almost there if you guys want to get started.
Okay. Are you there, Renee?
I am.
Okay, so let's go on to the first question here. When you are taking a sample size of n equals 5, what is the shape of the distribution of means, histogram, when the parent population is right skewed? Huh. Well, let's go in here then. Because that's something that I was actually questioning as I was watching the videos and looking into this. I was a little confused. Okay. So I'm trying to figure out if the skew is equal to the large skew, and that's all I'm looking for. Well, you know what? Let's open this up then. No, I want to go skewed the other way. No.
I'm trying to look for it on the text.
I want to skew it the other way. Skew it. No, no, that's not what I wanted. What are you doing?
So when it's talking about the size of n is equal to 5, it's talking about the sample, right?
Yeah. Okay, well, I think that if it's right skewed, then it's going to be right skewed in the bottom one too.
This is one thing that I am a little bit confused when it says parent population. What's it talking
Yeah.
about there?
So basically, all of your sample population or sample probabilities or things like that are going to be taken from a bigger one. So we have the bigger one up top, and then the one down below it, the one that we're working on, is the sample. So out of 1,000 people, we take a survey of 30 of them, and that will give us what we're looking at. So the sample mean and the sample distribution will be of those 30 rather than from the 100 that we've already taken it from.
Okay.
Okay. So I'm looking at the sampling distribution things, and not uniform, I want it skewed. What I'm going to do is I'm just going to throw this in here. Let's go back over here. To me, it looks like it's going to be pretty much skewed in the same direction that it says. Because I'm looking at this here. Let me open this up.
How can you tell with just 5 samples?
I know, and that's what makes it difficult. I'm just going through as many 5s as possible. So as you can see, it continues over.
Yeah, I understand that, but in the question, does it insinuate that you do it over and over and over again?
No, that's the hard part. Is it just says when you're taking a sample size of 5, what is the shape of the distribution of means histogram when the parent population is right skewed?
Okay, so you skew it right, you set it to 5, and you hit it once, and it could be anywhere along that.
Yeah, so here's my skewed left, and this is what happens when I have the 5.
Yeah, it's just random.
Yeah.
It's impossible to tell with just 5 samples.
So I put another 5, and it just seems to appear like this. It seems more like it's right skewed. Or, well, left skewed, sorry. No, right skewed.
Put in 10,000.
Gives us a pretty normal curve.
Right. See, that's the thing, though. It has to do with the number or the volume.
Yeah. Do 100,000 and pretty much stays the same. What I'm going to say is I have a feeling that
Hold on, go back to that other screen, the sample distribution.
Mm-hmm.
I think that what it means here, when it says n equals to 5, you see where the mean, right below the mean, it says n equals to 5. I think that's where the 5 should go, not necessarily just 5 samples, because it's talking about the n being equal to 5. So it doesn't matter. I don't think it matters how many samples we click on, 5, 10,000, or 100,000, as long as we have the mean on the n5. Because that I was just watching. Because I was just watching one of the videos right before we came to the meeting. I was watching, if I'm not mistaken, it was the first video, and he was explaining that that the n. He was giving some examples, and then he was making his work on it. So whatever the question asked for, the number of the n equals to whatever, he clicked on the samples, and then he showed that if it was normal, right, or left skewed. So I think in this case, it doesn't matter if you click on 1,000, 10,000, or 100,000, as long as we have the n equals to 5 on the mean.
Okay.
Because it's saying the sample size, not how many samples.
So the question says when you are taking a sample size of n equals 5, what is the shape of the distribution of means when the parent population is right skewed? So that means the little tail goes to the right. I feel like taking a small one of about 5 wouldn't make it normal, because it comes to normal as the sample size increases. So I would assume that it's right skewed, because the parent is right. Okay.
If I set mean as n equal 5, and I click on 10,000, it looks pretty normal.
I'm gonna go with normal on this one.
Yeah, because under mean you have n equals 5, and then above that on the sample data, it doesn't tell us how many samples are taken.
Exactly.
Choose whichever. So if you choose 100,000 samples, it's really quite normal looking.
Hmm.
The problem comes when you only have a few samples.
So the next question is the same one, and if you go to that same page that you were using here a minute ago, we're only changing the mean from 5 to 100 and then looking at it again.
Oh.
How do you change the mean to 100? Mine only goes to 25.
Oh.
Where did I even go to? I don't even remember how I got there. It's depressing. Oh, there it is.
Oh.
This population for which samples are taken, the mean of the distribution can be small to the line. Second histogram. Okay. So right skewed, go away email. And we take a sample of n equals 5. Distribution of means n equals 5. So we'll take a sample of 5. We'll just take a couple of samples. It seems like right here it has a little bit of a right skew from just a few samples. The sample size n equals 5. What is the shape of the distribution?
Hold on, guys.
Okay.
Seems like this is really complicated.
Let me look at the homework again to see if there was a similar question. I don't remember one exactly like this, but we'll see.
Yeah.
Yeah, I don't see another question like this in the homework. Oh, wait, we're on 6, aren't we?
You know what? I think this is a trick. If question 3 is that one, question 4 is 100 size sample size. We know that once it hits 30, it's a normal. So obviously question 4 is going to have a normal distribution. Since it's such a small one, I have a feeling that it's going to be a right skew on question number 3 because it's a small sample size.
I'm really surprised that they don't have a option there for it's impossible to determine. You know?
I mean, with a small size,
with that small sample size. So you're going to go on question 3 skewed right.
I'm going to say that one because since it tends to follow the parent, because obviously the larger amount of numbers comes from the left-hand side. So you're going to get a skewed right in that one until it starts to get to a big sample size. Because once you hit a big sample size, that's when you start getting the normal one again.
And then on 100, you're choosing normal. I understand. I understand why you're choosing that, and I think that's. We just got to convince Renee.
Yeah.
So let me go back to the book. I'm pulling this information from a particular section talking about the central limit theorem. In the third bullet point in 3.1, when is X normal? It says if the parent population is almost normal, then the sample size of 5 will probably be sufficient to assure that X will be approximately normally distributed. If the parent population is heavily skewed, then it will require a larger sample size to be assured that X will be normally distributed. For most moderately skewed distributions, a sample size of around 30 is traditionally thought to be sufficiently large to assure that X will be approximately normally distributed.
So we click that button 6 times. And that's going to give us a good example.
Not exactly. Because it's taking a sample size of 5. So it depends which number are you talking about, or which button?
The sample, the one that says 5.
Okay, so let me do this really quickly.
Because
I'll show
because it's saying that if the sample is too small, a sample of 30 would give you enough information to get a solution.
So there are 2 buttons. There's the animated version that takes a sample of 5 and gives you the distribution of mean. This is what it gives you as 1. So when we click 5, that's the 5 samples of 5.
So that's 25.
So that's why it seems to appear normal. That's what I'm getting. So if we do
and it does in the beginning seem to skew right.
This one is really strange. I don't know why. But if you add 5, you'll notice how more of the numbers start appearing to the left, and then there's those random few off to the right of it. And then the more and more you get, it starts to become more and more normal, and then ultimately it becomes normal with 10,000.
Okay. Well, it's a good thing we have to
yeah, that's the main reason. And I'll go ahead and submit mine first.
I think we're on the right track, though. I think that they're just trying to drive home the point that a sample of less than 30 is not going to
it's not
the population.
It's not going to bring a normal distribution,
right,
unless the parent population is normal, which is what the law was telling us, or what the central limit theorem was telling us.
Right.
So that's why I made my decision on the skewing, because it specifically says that unless the parent population is normal, it's going to require a large number of samples to make it normal.
To make the sample normal.
Yeah, to make the sample normal, the sample mean and all that.
Right. Right. But because it's not normal and the sample size is below 30, then it's going to be skewed.
Yeah. Now, to the right or to the left, I'm basing that answer on the fact that the parent was skewed right. So I'm assuming that the population, or the sample mean, the sample would also have the shape of the parent.
Right. And then on question 4, because we're taking 100 samples, we say, well, that's enough to get a normal curve.
Yep. Okay.
Okay, number 5. This one's funny because this one, it actually says it on the central limit theorem. It says if the parent population is normally distributed, then a size 5 should be enough to cause it to be normal. So I'm going to say normal
Right.
on that one.
Would you repeat that again, please,
Yeah.
Kevin? Because
Yeah, sorry.
you're breaking up.
When you are taking a sample size of n equals 5, what is the shape of the distribution of means histogram when the parent population is normally distributed? In the book, underneath the central limit theorem, it says if the parent population is almost normal, then a sample size of n equals 5 will probably be sufficient to assure that x will be approximately normally distributed.
Okay.
Right. It's what we were talking about before we got started, is that you either have to have a large sample size or the knowledge that the parent is in a normal curve. If you don't have both of those, then it's chances are it's not going to be normal. Or if you don't have either of those, I should say. Okay, I'll read the next one. Are you ready to continue, Renee?
I am. Thank you.
Okay. When you are taking a sample size of n equals 100, what is the shape of the distribution of means histogram when the parent population is normally distributed? So here we have a sample size that's great enough to get a normally distributed result, and the parent is also normally distributed. So there's a pretty good likelihood that you're going to get normal result.
That's what I'm assuming.
When we first got started is we weren't used to the way that these questions were worded.
Mm-hmm. So number 7, when would the distribution of means be normally distributed? Choose all correct responses. Data are drawn from a population that is normally distributed and the sample size is small. Data are drawn from a population that is normally distributed and sample size is large. Data are drawn from a population that is right-skewed and the sample size is small. And then data are drawn from a population that is right-skewed and sample size is large. So I say B and D.
Okay, I'm going to go with A, B, and D.
I also think it's A, B, and D.
Mm-hmm.
And a reason I think it's A, Renee, is because even though we have a small sample size, we know it's coming from a population that's normally distributed. So we would expect the sample to also be normally distributed.
So when the parent population is normally distributed, the likelihood of the distribution being normal it's accurate. Like that's the answer.
Yeah.
Yeah.
Right.
Okay. I have a feeling that the questions right now are dealing more with the central limit theorem. Yeah, because they're talking about distribution, so they're talking about the central limit theorem. Soon.
Well, I think it's also talking about large numbers when they bring up the sample size.
The central limit theorem.
Are you looking at question 8, Kevin?
Yeah. Sorry, I'm supposed to be reading it, aren't I?
Yeah.
Sorry.
Yeah, read.
Which of the following gives the best explanation of the central limit theorem? If the parent population from which the data are drawn is normally distributed, then the sample mean x will follow a normal distribution. For bell-shaped data, approximately 68% of the data will be within 1 standard deviation of the mean, about 95% of the data will be within 2 standard deviations of the mean, and approximately 99.7% of the data will be within 3 standard deviations of the mean. I think we can rule that one out. If the sample size is large, the sample mean x will be close to the population mean mu. If the sample size is large, the shape of the distribution of sample means will be approximately normal. I'm going to go with the last one.
Yep.
Mm-hmm.
Yeah, I think that rule does deal more with the shape.
Mm-hmm. Because you go in
Anything
here,
else?
yeah, you go in here and it says that the central limit theorem states that in the sample size, if the sample size is large, that x will be approximately normal. The law of large numbers states that the sample mean x will be close to mu, or the mean.
I got the next one.
Okay.
Use the following information
And
to
sorry, I apologize. In answer C, if the sample size is large, the sample mean blah 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 blah. That one would be the explanation for the law of large numbers.
Yeah.
Wouldn't
Yes.
it? Yeah.
I agree. Okay, we ready?
Yes.
Mm-hmm.
All right, use the following information to answer the next 4 questions. X be the random variable with the population mean of 10. Sales chart here.
Handy dandy notebook.
Population mean of 10. The standard deviation of 6. And suppose a sample size of 36.
So,
okay. I think the first thing we need to do is solve. Well, actually, the first thing we need to do is keep rating, huh? Okay. 9. What is the mean of the distribution of sample means?
mm-hmm.
Okay.
And that's 10.
I don't think so. I think it's asking for the mean of the sample, not the mean of the population.
Yeah,
So in order to do that, I think the first step is that we have to figure out the z-score, right? No, don't we have to have either the z-score or x. So what is So I don't see a z-score or x. So how do we figure out what the
okay, what was the mean again?
So there's another formula that the guy talked in the first video. And the formula is the standard deviation divided by the square root of the sample will give you the standard deviation of the distribution.
sample?
Yep.
So, okay, so basically we just ignore x and the standard deviation of the population, and we just divide 6 by the square root of 36?
Yes.
Okay. So let me pull out my calculator here and figure out what the square root of
Where's my square root?
so slow right now. Okay. 36 squared 6 would be then
So
6 divided by
6,
6, right?
correct. So it would be 1. So the answer to number 10 is 1.
The answer is 1.
Hold on. Did we skip number 9?
If which I'm assuming it is, This looks very similar to the problems that he was going over in the video number 1, lesson 6, part 1. This is a very similar problem of what he was going over. I think the question to number 9 is just what the mean is. So I would say 10. And then question number 10, it's that formula that we just used.
So 10 is the population mean. Look at above, it says the population mean equals 10. And the question number 9 is asking for the sample mean, not the population mean.
Yeah, the mean of the distribution of sample mean.
So, right, so I don't think it's going to be 10. I think it's going to be standard deviation divided by sample size, n.
Okay, can you pull up your screen really quickly? I'm already confused as to what's going on, and I don't have
My screen?
Yeah. Give me 1 second.
Come on.
Sorry, my notebook was behind my computer. Rude. Okay.
Okay. So where did it go? Hang on. Oh, I know what the problem is. Okay. Here's the question. And so Renee was saying, so the question is, what is the mean of the distribution sample means? And Renee was saying, well, I think it's 10 because above it says the mean is 10.
Yeah.
But my problem with that is that 10 is the population mean, not the distribution sample mean.
Okay, give me 1 second to read this. So this is section 4 of the chapter. It says the following facts are always true. They do not depend on the central limit theorem. They do not depend on the sample size. These facts hold for the sample mean x of any simple random sample of size n drawn from a population with mean u or mu and standard deviation sigma. The mean of the sample means is always mu. So if mu is 10, that would mean that the mean of the sample means has to be 10, just like Renee was saying. These are 2 rules. And the second one is the standard deviation of sample means is sigma divided by the square root of n. Let me show this really quickly. Can I share my screen? Is it going to do double share screen? No.
No, I quit mine.
Okay. This right here. And then it also says down here, remember, these facts are always true. It never changes.
I hate ebooks. I can't. I like hard copies.
So do we have that?
It's really hard to read on your screen. I mean, I know I can pull it up on my side, but
can I? Does this help at all?
Yeah.
So the following facts are always true. The mean of the sample mean is mu, and the standard deviation of the sample means is sigma divided by the square root of n.
Okay. So it's just a matter of me understanding how things are labeled, I guess.
Yeah. That's okay. I didn't really know that either, not until I looked at this, because it just passes my mind.
So the mean of the distribution sample mean is the same thing as the population mean.
Mm-hmm.
Okay.
It doesn't. I don't think it matters what says right before mean or mu, because mu will always be the mean.
Mm-hmm.
So I'm not sure if that's what's throwing it off, but mu it will always be the mean, regardless of what wording they use right behind it.
Think about the simulations you have observed. The mean of sample means was always aligned with mu. Also, if you took samples larger than n equals 1, the standard deviation of sample means was always smaller than sigma.
Okay.
Yeah,
Question.
there we go. Here's the question. Am I still sharing?
Yeah.
Yes. Okay.
Well, not anymore.
Here's an example. The amount of time passengers spend waiting for a bus on a particular urban route follows a distribution that has a mean of 8.7 minutes. What is the mean of the distribution of all possible sample means? 8.7 minutes.
Okay.
So I'm gonna agree with Renee on this one, and just say
Gotcha.
stick with it.
Okay.
Now your cool handy dandy thingamajigger will really come in handy for 10.
What is the standard deviation of the distribution sample means? Well, I don't know about that because we don't have the value.
Number 10.
So
number
we
10
have
is
sigma, right?
1.
Yeah.
Yes,
So we have 6 over 30, the square root of 36.
that's correct.
Right. Which that one I think is 1. That's what I was trying to do in question 9.
So we'll have that one right again. So 9 and 10. Kudos to Renee for being right on both of those.
Okay.
It's because I went over the material before the meeting. I usually don't have time, but
Yeah. Okay. Now it says regardless of the distribution. I'm sorry. No, Renee, it's your turn, not mine.
regardless of the distribution of the population, if the sample size is larger than n greater, I don't know what that symbol is, 30,
Yeah.
what would be the shape distribution of the sample mean? So wouldn't you figure that anything over 30 would be normal?
Correct.
That's what I remember.
Yeah, it should be normal.
And which theorem applies to this particular question?
Shape distribution, it would be the central limit.
I agree. So in question 12, go ahead and select central limit.
Because it's talking about the distribution of the means, it's not talking about, the means in particular.
Well, that's all the questions we have. We didn't really get into a lot of equations.
Yeah, no, I think they want us to understand the laws because in the next chapters, that's when we're going to be going through a lot of numbers.
Do either of you know when we have a test?
Next week. Should be.
And how do we take those tests? They haven't talked
Fine.
anything about proctoring or anything like that.
No, some classes don't do that. And I don't know why. I think it's because they really trust us. That's really cool, actually. I think that's awesome because it's a lot of trust that they have in us. But at the same time, I don't think he said anything about proctoring. So we're probably just going to be told, don't do this, don't use
Don't
this,
cheat.
don't use this. Yeah.
Or this is what you can use or whatever.
Welcome to Mormons, having us take tests by ourselves and trusting the nonsense out of us.
Yeah.
All right.
Well, a lot of times, depending on the exam, you can use your notes.
Mm-hmm. That too. Let me submit the quiz then.
So the only one that we might have or that we have different at this point is question 3, either right skewed or normal, right?
Yeah. So let me submit it, and we'll see. Okay. All right, there's 100%. So the answer is
Right.
skewed right for number 3. Now, again, just to cover that, the reason why we made that decision is because the number is small and the parent is already right skewed.
I see. So that
Mhm.
that's the same reason why we chose A, B, D on that other question,
Exactly.
because of the answer A, that description.
Yep.
Yeah.
Okay. I feel like
So
Tomorrow,
yeah, I really need to go to bed.
okay.
I really don't want to accidentally wake him up. I think he
Okay.
passed out already. So,
Okay.
but
So what time tomorrow? Same time?
I can meet
I
earlier.
have
6 would be best for me. That way I can come home and at least have half an hour to review the material to be
Mhm.
ready for the test or for the quiz.
that would be what, 9 o'clock your time? No, 8 o'clock your time, Kevin.
Uh-huh. And I can do that. It'll give me some time to do some homework too,
Okay.
and use the bath.
So same time tomorrow that we did today.
Yeah, that should be fine.
So then is that going to be like our schedule on Tuesdays at 6 and then Wednesday we play it, I guess? Or
Yeah.
Yeah, that's what I'm taking it as.
Okay.
This,
Mhm.
I just have one extra question. What's your guys' major?
Wait, what?
What's you guys' major?
Oh, my major is entrepreneurial business.
And Brett,
Also,
have you guys taken Business 383?
yes, the nightmare.
It is
I
a
don't think I
nightmare.
have.
It is a nightmare. We're starting week 4 and I haven't come up with what I'm selling. So
383.
What were your
Yeah.
three
Yeah,
ideas?
no.
What were your 3 ideas?
my 3, well, do you want to stop recording? This is
Oh
Yeah,
yeah.
let me stop recording.